electron config of ions. So let's start with the ones that follow the rules. Let's start with the good guys. All right, and we'll start with these guys follow the rules and these guys follow the rules over here. So you remember way back in the day I had you memorize, oh, these are all +1 ions, these are all +2 ions, these are -1 ions, these are -2 ions, these are -3 ions. Aluminum is always a +3 ion. All right, we had you memorize that. If we had introduced all these quantum numbers back in the beginning of the semester, you wouldn't have had to memorize that because you would understand where those come from, and we'll talk about that right now. So let's take a look at sodium. Remember, the sodium electron configuration is neon 3s1. We know that sodium likes to be a +1 charge. +1 means I've lost 1 electron. Where does that electron come from? The electron comes from the valence shell. So that 1 electron that's sitting in a 3s orbital, it wants to lose that electron. It does lose that electron. So the electron configuration for sodium is just neon. It lost the 3s electron. Let's look at beryllium. Beryllium, the atom is helium 2s2. You remember beryllium is always a 2+ ion. Where does that electron come from? It comes from the 2s orbital. It comes from the valence shell. So its configuration is helium. Let's look at strontium. Strontium is down here on the periodic table, number 38. It is, go back to the prior one, krypton, 5s2. It's in the second period of the periodic table, so strontium likes to form 2+ ions. It comes out of the 2s, therefore its electron configuration is krypton. All right, you see a trend emerging. These are cations so far, right? All the cations like to form noble gas configurations, at least the ones from here. All right, let's take an anion. Let's take fluorine. Fluorine, we know, is helium 2s2, 2p5, and we know that fluorine always forms a -1 charge. That means 1 extra electron. Where does the electron go? Well, there's 1 slot left in the p orbitals, and that's exactly where it goes. So it's actually going to move 1 this way, so it forms a neon electron configuration. Sulfur is neon 3s2, 3p4. It likes to form a -2 ion, which means it's going to go 1, 2. It's going to put 2 extra electrons in. It's going to form an argon configuration. All right, so do you see these anions also like to form noble gases? It's called a noble gas configuration. And let's see if I have 2 that are drawn the same. Yeah, sodium ions and fluorine ions both have a neon configuration. These are called isoelectronic. Same electron configuration. So you notice what happens. These elements like to form noble gas configurations. That's why they're energetically stable. That's why they like to do that. Okay. That explains the S block, and that explains the P block ions. Now, these, as I mentioned, are the bad boys. Okay? The transition metals are the ones that are always the exceptions. So let's take a look at the transition metals. Let's take vanadium as my example. Regular vanadium is not one of the exceptions. It's got an argon configuration, and it's going to be 4s2, 3d1, 2, 3, 3d3. Now, if you remember, I told you when we name compounds ions, with transition metals, we need to tell the Roman numeral of the ion because there's several different oxidation states that are possible. Vanadium can form +1, +2, or +3 ions. So how do we deal with this? So here's the rule. The rule is transition metal ions, the electrons come out of the s orbital first, then the d orbital. Okay, this is not a trick. They all do this. I guarantee you some of you are going to get this wrong on the exam. You're going to forget this rule. Transition metals, when you make ions, the electrons first come out of the s orbital, then they come out of the d orbital, which means the configuration for vanadium is argon 4s1, 3d3. Vanadium 2+ is argon 3d3, and vanadium 3+ is argon 3d2. Okay, you see what's happening? Has 2 s electrons originally. I start pulling s electrons out. There is no s electrons here. Then I begin removing the d electrons. All right, it's not a trick. It's not an exception. It's just the way transition metals do it. That's the way nature does it. It's more energetically stable to remove the electrons from the s orbitals than it is from the d. Those d orbitals are stable chemically. Having those spin paired electrons, nature likes that. It's easier to take the s orbitals out. Okay? So let's say this again. Transition metals, when you form ions from them, the electrons first come out of the s orbital, then come out of the d orbital. Once we know that, we can write the electron configurations. They're not trick configurations. So let's take iron as an example. Iron also has an argon core, and there's 2 main ions for iron, 2+ and a 3+. So the metal itself, so I always start by writing the metal down. The metal itself is argon, it's in the 4th period, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6, which means argon 2+, I pulled 2 electrons out. It's going to take them out of there. So it's argon 3d6, and iron 3+ is argon 3d5. All right, let's review what we've talked about so far. We talked about the shapes of orbitals. We reminded ourselves of the different quantum numbers, how we get those shapes. We've talked about electron configurations, the difference between a valence electron and a core electron. We can write as a form of notation. We can write the core electrons as a noble gas configuration, and then we can write the valence electrons following the noble gas configuration. We noted that these are s block elements, these are p block elements, these are d block elements, and these are f block elements. We also noted that the s and p, whatever row of the periodic table an element is in, that's what principal quantum number is. So this is row 4, these are going to be 4, these are also going to be 4. This is n-1, and this is n-2. We also remember that these 2 guys get inserted in the 6th and 7th row. Okay? We also talked about writing electron configurations for ions. If they come from groups 1 and 2, or the p block elements, they're going to form a noble gas configuration. If they come from a transition metal, do you notice? None of these have a noble gas configuration. The reason is you have to take too many electrons off. It isn't very common to strip 6 electrons off of an atom, or 7 electrons or something. And we also noted that the electrons come out of the s orbitals first. To summarize the quantum numbers, that n number tells you how big is the orbital. The L number tells us the shape. The m sub L tells us the orientation in space. And the spin number tells us the direction the electron is spinning.